my talk gonna address the questions about how black holes, the astrophysical black holes, power jets, multi-wavelength flares in near-infrared and X-rays, and also how a very spectacular lightning can happen right at the edge of the black hole near the event horizon. This is the work that I've started doing when I was an Einstein Fellow at Berkeley, and largely continued as a RS at Flatiron. So Flatiron has played a big role in supporting this work, as well as grants from National Science Foundation, in particular 10 Big Ideas and Multi-Messenger Astrophysics program. This is a work done in collaboration with many people. Kyle Parfait and Benoit Cerruti are my long-term collaborators, and more junior people whom you're going to learn during the talk heavily contribute to this work. So I'm going to jump right on and say what is the astrophysics that we are interested in. We are interested in black holes. They're usually located in the center of galaxies. And in particular for this talk, let's forget about all the gazillions of black holes living out there and just focus on two most interesting ones. The black hole in the galactic center, the supermassive black hole in the center of our own galaxy, Sagittarius A star. It's basically a black hole sitting right there. This is an infrared view of our Milky Way galaxy. And this is a massive source of multi-wavelengths continuous radiation that we know is out there for pretty long already. We also know that it's a supermassive black hole whose mass is around 4 million solar masses. We know this by tracking trajectories of the stars around this supermassive black hole. This is a very accurate measurement that got people who did it a Nobel Prize this year. So we know the mass of this black hole, and we know the size of it thus far, because the mass of the black hole is the most important parameter, and it sets a scale. It sets a scale at which, if you launch a photon, let's say, or any massive particle, it would not be able to escape the very strong gravity of the black hole. So this is what we call a gravitational radius of the black hole. It's proportional to its mass, and for this supermassive black hole in Sagittarius, its size is 6 million kilometers. So we have a 6 million kilometers object sitting right in the center of our galaxy and powering very interesting activity. The stars that fly around the supermassive black hole blow winds. So we know that our own sun blows a wind of plasma, the stream of electrons and protons and electromagnetic fields. And all of the stars blow similar winds that collide with each other, fly around, and eventually accrete onto this black hole. So this is what we call an accretion flow into the black hole. And in the case of Sagittarius A star, we actually know what feeds this black hole. It's a flow from several stars that rotate around. Recently, there has been a spectacular observation by infrared gravity interferometer, which is so accurate that it's able to resolve the trajectories of hotspots, big hotspots of plasma orbiting around the black hole on an orbit and shining in near infrared and X-rays. So this is a light curve of this near infrared flare. The I and Q are different Stokes parameters for this light. So we basically see flashes of near infrared light that goes for basically a time of an order of an hour. And then the recurrence time of these flares is of order of 6 hours for near infrared and 12 to 24 hours in X-rays. So every half a day, this black hole launches a gigantic, the gigantic flare of light that we see on Earth. And it comes from a very localized region. With this modern observations, we're able to resolve the size of this region, and the result is basically comparable to the size of the event horizon. What's interesting for modeling this event is that this plasma is very, very unusual, although it's very common in astrophysics. Since this source, we know the properties of the source, we can estimate the strength of the magnetic field and the plasma density that is out there and shining in quiescence via synchrotron radiation. We know its temperature roughly, and we can estimate the mean free path of charged particles in this plasma. So basically, this accreting flow consists of electrons and protons, and they have to travel certain distance before they could collide with each other via electromagnetic interaction. So since the density is so low, the distance for electron to see another charged particle is basically much, much larger than the size of the accreting black hole. So the plasma is what we call collisionless. So basically the particles don't interact with each other directly. They interact with the whole ensemble of these particles via the electromagnetic field that they create collectively. So this is a very important point for the upcoming slides. That remember that these particles are not really interacting with each other; they're interacting with the whole ensemble. However, there is a smaller scale in the problem, which is the Larmor radius of this charged particle. So the Larmor radius is basically a scale that electron travels when it gyrates around the magnetic field. So everyone probably took a freshman E&M, and they know that if you put a particle, the electron, a positron, or a proton into a magnetic field, it would stream along this magnetic field and also gyrate around. So the scale of this gyration is what we call a Larmor radius, and this Larmor radius near Sagittarius A star is very small. It's much, much, much smaller than the size of the black hole horizon. So although particles don't see each other directly, they're tied to magnetic field lines. They cannot really cross them because the scale at which they cross them is so small compared to the macroscopic scales. So this has been a first black hole that we're interested in. And of course, the second black hole is a black hole in a nearby galaxy M87. This black hole has caught a lot of attention in 2019 when Event Horizon Collaboration released their interferometric radio image, which is taken at 1.3 millimeters, basically radio observations. What this picture basically reveals is that there is a supermassive black hole sitting right there, and there is a hot flow of gas, of plasma around this black hole that emits light that we see at radio frequency with this Event Horizon telescope. So at this resolution, unfortunately, we cannot yet learn anything particularly interesting about the properties of space-time around the black hole or dynamics of plasma, really, because this image fits with really a lot of models that we can produce studying the dynamics of this plasma. However, this would very soon become very interesting for constraining both the plasma physics and general relativity. So this is an interesting time to start thinking how we can model this accretion flows more properly. So M87 has similar conditions compared to Sagittarius A star. We don't know exactly how it's fed from large scales. We cannot resolve individual stars or whatever powers the flow of plasma onto a black hole, but we can roughly know the accretion rate, the rate at which the mass is brought into the black hole. We can know the density and roughly know the magnetic field. And we basically know that these conditions imply collisionless, very magnetized plasma flying around near the event horizon of a black hole and producing light. Compared to Sagittarius A star, there is also an interesting feature of this black hole that it powers a large-scale jet. So this jet is a flow of relativistic particles and perhaps also electromagnetic fields, which is observed on scales much larger than the event horizon itself. So the jet extends to 1.5 kiloparsec from this black hole, which is enormously larger compared to the size of the black hole given by its gravitational radius, which is roughly 2 times 10 to the 10 kilometers. So orders of magnitude smaller than the size of this jet. So this basically raises an interesting question of how those jets are launched. What powers them? Are they powered by the black hole, or are they powered by the electromagnetic fields around the black hole? Finally, this M87 is known to produce tremendous flares of TeV photons, very energetic photons, which are produced somehow very close to the event horizon. And we know that the variability of this emission is even smaller compared to the light crossing time of the event horizon. So the emitting source somehow is even smaller than the size of the black hole. It's sitting very close somehow, and it produces enormous flashes of photons, but we don't yet know how it's produced. So this outlines the basic questions that I would want to address with this research. how this image is produced, like what powers the, what energizes the particles that produce this light, how the jets from the supermassive black holes are launched, and finally, what powers these flares. So now I'm done with the astrophysical introduction, and I could do something that I really enjoy doing. I enjoy doing theoretical physics. And theoretical physics for the theoretical physics framework for this objects is actually well known, and it's known as kinetic plasma physics. So the basic mathematical object that we want to understand with this plasma is what we call a distribution function. So a distribution function contains all of the information about the plasma. Basically, it tells you what is the probability to find a particle with a velocity v at the position x around, let's say, a black hole. So once we know this, we know all the energy that is stored in the plasma that can radiate the photons. And from that information, we could, in principle, calculate the emission signature directly. So ultimately, what we want to know is we want to know a distribution function of electrons, which we know that these are the electrons that produce observed light. Protons are very heavy; they cannot radiate efficiently. So what we ultimately want to know is the distribution function of the electrons. If you want to do a very first principle theory, this distribution function would depend on coordinate and velocity of each particle available in the system. This is so much information that you cannot actually process it. And the zero-order approximation that has been done by Landau and Vlasov and mathematically described by what's called the BBJKY hierarchy by Boголюбов, Green, and Kirkwood and others, is that if the plasma is sufficiently dense, you can actually forget about this all other particles and combine the information into this one object, which is called the single particle distribution function. So from that, we basically have this equation, which is nothing like the continuity equation for a flow of distribution function in the 6-dimensional space. So this distribution function depends on the coordinate and the velocity. This term defines how it's changing in time. This defines the advection of the distribution function with the velocity of a plasma flow. And this is a force acting on the plasma. This is basically a Lorentz force. We know that charged particles are subject to a force driven by the electric and the magnetic field, and the total force is what we call a Lorentz force. So this equation equals to the what we call a collision operator, the term which describes Coulomb collisions between the electrons and protons and electrons with each other. We know that for this plasma around the black hole, this term is really small, so we can basically neglect that. So this equals to 0 is the equation that drives evolution of our distribution function. The electromagnetic fields are obeyed by typical Maxwell's equations. So you probably know these equations. They basically tell that magnetic field has no charges. In mathematical language, this translates into divergence of B equals to 0. Electric field on the same side has sources, charged particles. They all seed electric field. And divergence of this electric field is equals to the charge density. This is a charge density that you can compute from the distribution function. Basically, you integrate this distribution function over the velocity space, and this gives you a charge of a given charge species at a given position. This you can feed into this Maxwell's equation and find the electric field. What we do numerically, though, is that we evolve not these two equations, but time-dependent Maxwell's equations. We evolve what's called the Faraday law, which tells you that a changing electromagnetic field in space and time sort of interchanges between each other. The changing electric field can produce magnetic field, which is this equation, and the changing magnetic field can produce electric field. And also electric field can be produced by currents, which is this term. So this term basically couples the evolution of plasma with the electromagnetic field. You can calculate the currents from the distribution function and the velocity, and this current is a source term for this equation. What's the key here is that these equations are actually not independent. They're basically initial conditions to these equations, because if you take a divergence of this equation, divergence of a curl is 0. So this basically tells that time derivative of divergence of B is 0 if this equation is fulfilled. If it's 0 from the beginning, it will be always fulfilled if our numerical scheme integrates this equation accurately. So we don't need actually this equation. And similarly, we don't need this equation ultimately. So we're only evolving this two and the equation for the plasma. So naively, you would say that this is the answer and this is what we should be doing. Practically, this is a very challenging task. So the equations that you need to evolve are sitting in a 6-dimensional space. At each point in coordinate space, you have 3 components of the velocity. This is a 6-dimensional space. So although I will describe a well-known method that can integrate these equations easier, they're still challenging. So what people have been doing for last 2 decades is that they've been ignoring this, they're ignoring the real conditions around astrophysical black holes and saying that let's forget about the collisionless nature of this plasma and let's take a simpler approach, which is called a fluid approach. So instead of describing the plasma with this complicated object known as a distribution function, we will take in a few assumptions which will lead us to much simpler equations. So first assumption is that let's assume that there is practically so much plasma that the charge density is very small compared to the overall density of the plasma. This is simply realized in this accretion flow around the black hole. It's not true in the jet, and it may not be true at all in the jet, but still in the bulk of the flow, it's a good approximation. Second approximation is that we'll forget about the collisionless nature at all and say that the plasma is actually collisional, meaning that the mean free path of the particles is much smaller compared to the size of the black hole. And this will basically lead us to the very simple solution of this equation for the distribution function, which is known as the Maxwellian distribution. So basically, in a steady state, if you allow plasma particles to collide, they will reach an equilibrium, which is known as a Maxwell distribution, which is well known in not only in physics, but also in statistics. This is a Gaussian distribution that allows to find basically a probability for a plasma particle to have a given velocity v. This Maxwellian distribution is a function of only one parameter, the temperature, and this basically allows to reduce all of the information about the plasma only into a few numbers. So these few numbers will be the temperature, the density of the plasma, the mean velocity of the plasma, and the magnetic field at a given position. You don't even need the electric field in these approximations, because if you assume that the plasma is an ideal conductor, which actually is a good assumption if the density of the plasma is large enough, then you can find out that in a frame moving with the plasma, there will be no electric field. This is a pretty easy to understand assumption, because if you would think what the plasma would do if you would immerse it into electric field, would be that electrons would go like in the opposite direction with respect to the electric field. Protons would go along the electric field, and they would create an electric field in a direction opposite to this externally imposed electric field. So basically what the plasma wants to do, it wants to screen this electric field, which wants to charge separate the different species. So this is true in the frame of a conductor. If you jump back with a Lorentz transformation into a frame that that is stationary and the plasma is moving with respect to this frame with a mean velocity v, you will find this connection between electric and magnetic field. So basically with this set of assumptions, we got rid of all of the information about the plasma except for this several quantities. It turns out it's a good approximation for large scale dynamics. And this is what people have been doing for quite a while. I will show you a few phenomena which definitely did not fit into this paradigm, but also I will show you how this approximation can actually be very useful if you want to understand large-scale dynamics in 3 dimensions. So a theoretical cartoon for the behavior of the plasma around the black holes has been known basically from late 70s by Roger Blanford and Znayak. Their seminal paper in 1977 basically laid a background picture of how we are now thinking about accretion flows onto black holes. So this cartoon basically shows in a picture what I told you before. There is a flow of charged particles, electrons, and ions that are rotating around the black hole and also falling into it. They're bringing magnetic field with them, and this magnetic field gets attracted into a black hole. So the major contribution that this paper did is that they described electromagnetic mechanism that can power jets. So if you bring the magnetic field onto a spinning black hole, it will basically do a very simple phenomenon known from Michael Faraday, known as a unipolar inductor. So in the Faraday's picture, he was thinking about a rotating conductor, which basically a conducting disk, which was rotating, which was threaded with a vertical field. So what this conducting disk will do is that it will induce electric field because it's rotating, and this electric field would launch a flow of electrons and protons from the surface of this conducting disk, and basically power a flow of electromagnetic field and charged particles from the surface of this conductor. So in the case of the black hole, there is no conductor. The event horizon is a no-go surface. You can go only into one direction. You can fall into the event horizon, but you cannot go out. However, rotating black holes have the surface which we call an ergosphere. So an ergosphere is a surface inside which, although you can still escape from the black hole, you won't, the gravity and the dynamics of the space-time drives any massive particle or a photon to co-rotate with the black hole. So any particle inside the ergosphere basically is dragged along to rotate alongside with the black hole. So for the spinning black holes that have this ergosphere, the space-time around the black hole basically does the same job as the rotating conductor does in the case of Faraday disk. It winds up the magnetic field that the accreting flow brings toward the black hole, and this flow of electromagnetic field can power jets. Sort of an elephant in the room here that has been realized by Blanford and Znayak, but has been forgot for a long time since then, is that the accretion flow can actually has very hard time penetrating into the region of this outflowing jet magnetic field lines. This is entirely because of this condition that I described in the beginning, that Larmor radius of charged particles is very small. If you put a charged particle right here, all it can do is that it could just go along the magnetic field, and it cannot cross magnetic field lines. So it cannot do a trajectory like this, for example. It cannot start here and end up being in this polar field lines that would power jets. So this brings to a natural conclusion that has to be some source of plasma which is not connected with the accretion flow, which powers the outflowing jets. And this paper realized what the source should be. Basically, the dragging of the magnetic field that the accretion flow brings to the black hole by the rotation of the space-time induces electric fields. I will show you mathematically how this happens later, but for now, all we need to understand is that rotating black holes, which were sort of supplied by the magnetic field from outer scales, create electric field. If I now drop one particle, let's say electron, in this electric field, it would be accelerated to very high energies right along the magnetic field lines, and then these particles would emit photons, which would collide with the photons produced by the accretion flow, and these two photon collisions would create an electron-positron pair. So this is a very simple process known from quantum electrodynamics, is that if you have two photons of sufficiently high energy, for example, let's say a GeV photon and a KeV photon, or an MeV photon and a MeV photon, they would collide with each other and create an electron-positron pair. So this electron-positron pair, which is depicted here, is now also picked up by the electric field. Electrons would go one way, positrons would go another way. They would start getting accelerated, emitting new photons, and these new photons would collide again with the photons from the accretion disk and create new pairs. So this is what I call a QED lightning. So instantaneously, just out of one particle that I dropped inside this jet region, you would end up with plenty of particles, plenty of electron-positron pairs that would outflow along the jet field lines. So this phenomena cannot be described in the fluid picture that I just outlined to you before, basically because it violates all the assumptions. I started this description by saying that there is a strong electric field along the magnetic field. This violates the fluid assumption. The whole nature of this intermittent lightning-like production of particles sort of assumes that the process goes through time periods where there are no particles at all. So there is no plasma, it's just vacuum. So vacuum is obviously not a plasma, so it cannot be described as a fluid. So what we need is a fully self-consistent picture of how this process operates. This cartoon picture has been formalized with numerical simulations of this fluid equations known as magnetohydrodynamics. And they basically shown that in 3 dimensions, if you start with a big blob of matter far outside from the black hole, this blob of matter would distort itself into accreting flow, a disk of matter which rotates and falls into a black hole. And rotating black hole creates a outflow of electromagnetic field and particles into this jet region, just as Blanford and Znaik cartooned in 1977. So this is a result of a 3-dimensional simulation, which has been averaged out in the azimuthal direction, in the direction of rotation around the black hole. So in a 3D, in a real 3D system, this is a highly turbulent, very active environment. But if you averaged it out in the azimuthal direction, it actually looks very familiar to this cartoon. This is to bring this analogy of a Faraday disk closer. This is a nice YouTube video that you can find on the web. So basically, the system operates like a Faraday disk, but in inverse. So here you have a Duracell and you have a circuit, and this is a magnet. So once you plug in a battery here, it basically launches a current flow along the circuit. And since you have a magnetic field, you start to have a force which acts on this Duracell battery, and it starts spinning. So this is basically a black hole in reverse. It is supplied with a magnetic field and supplied with a current circuit, and then it starts spinning. Black hole does the opposite. It's supplied with a magnetic field from the outside accreting flow, and it induces voltage, and this drives current along the circuit. So current along the circuit is basically a flow of electromagnetic field and charged particles along the jet. So this finishes my long introduction and basically talks about more detail, focuses on phenomena that we want to understand. We want to understand how this image of the event horizon is produced by hot plasma near the event horizon, which unfortunately I'm not going to talk yet about in this talk because this is a very challenging problem. We don't yet know how to do this. Although I will tell you how these jets produce plasma and high energy flares, and also flares observed by gravity. So this is a numerical tool that we are using. I told you that the most fundamental framework is to model equations in 6 dimensions, the distribution function, depending on coordinates and the velocity. The way we simplify this is that we replace this continuum approach with the Monte Carlo approach. We basically reduce the continuum description via the distribution function into a description via a bunch of individual particles. We obviously cannot model the actual number of particles that are sitting around near the black hole, because this would blow even the most powerful computers available to us. So we are basically replacing an ensemble of particles near the black hole with what we call macro particles. So a big particle that is responsible for smaller particles that are flying around. And basically what we are solving is that we are again solving Maxwell's equations. Now they're formulated in curved space-time. you see here that not only changing electric field can produce a magnetic field, but also the rotation of the space-time, which is parameterized by this beta vector, can create a new electric field, which in case can create a new magnetic field. So for this process of lightning, what's important is that basically what we call a frame dragging, the dragging of magnetic field with the space-time induces an extra electric field compared to the case where the gravity would be not important. And this electric field drives all the dynamics near the event horizon. Each individual particle obeys these equations of motion. This is basically telling that the rate of change of the particle coordinate is given by its velocity. And you also have to take into account this effect of dragging of the inertial frames. And the rate of change of the particle momentum is described by the Lorentz force and basically the gravitational force. So this gravitational force is written in this obscure language, but basically this is just a general formulation of a gravitational force from the black hole. What the code does is that it operates on a grid, which is a two-dimensional grid with grid points at which we define electromagnetic fields. And then particles fly around on this grid. They create charge densities and the currents that are sources for this Maxwell's equations. And this electromagnetic field are sources for particle equations of motion. So this is a self-consistent system. Particle is going along by the action of the actual electromagnetic force, and the electromagnetic field is created by the motion of the charged particle self-consistently. So this is why it's complicated, because it's highly nonlinear. This important interplay between electromagnetic fields and particles is very important to understand their dynamics. So now I'm going to the most interesting results that we've been able to achieve in the last 2 years, basically while I'm at Flatiron. This has been the first general relativistic kinetic simulation of how jets could be launched, which was published in PRL, and the image got published on its cover, where we started with a very simple model when we assumed that there is this very highly spinning black hole in the center. The black region outlines the event horizon of this black hole. The green line here shows the ergosphere. Again, the ergosphere is basically a volume of space where the particle has to correlate with the black hole. And we assume that there is an initial magnetic field around this black hole. And in vacuum, this is a very interesting phenomenon that in vacuum, highly spinning black holes operate as superconductors. They want to expel any magnetic field out of the event horizon. And in early 2000s, that actually caught a lot of paradoxes about this Blanford and Znayak mechanism, because Blanford and Znayak assumed that all the magnetic field lines that go along, they actually penetrate through the ergosphere and the event horizon, so they can launch this flow of electromagnetic field and particles. If you just start in vacuum, this is not true. The highly spinning black hole will just push the magnetic field away, and no Blanford-Znayak mechanism would be possible. So we start in the state in vacuum and just start sprinkling plasma particles around, which in this case would be electrons and positrons. And we would see how this ensemble of electromagnetic field and charged particles would self-organize themselves into a self-consistent solution. So as I'm playing this video, you see that the magnetic field lines are deformed. They're dragged towards the event horizon. They're no longer pushed away. And basically, you find that all the field lines that penetrate the ergosphere, they also penetrate the event horizon. So this basically proves that once the plasma effects are taken into account, the original Blanford and Znayak picture is correct. All the field lines penetrating the ergosphere go through the event horizon and launch the flux of particles and electromagnetic fields to infinity. An interesting point you can see in the equatorial plane, you see some interesting dynamics of the density of both electrons and positrons. And you can also notice what the magnetic field does. So these contours are magnetic field lines, and you see that they basically get discontinuous around this equatorial surface. What you have here is that you have oppositely oriented magnetic field lines touching each other. So the magnetic field is going outside in the northern hemisphere and going back to the black hole in the southern hemisphere. So right at the equator, these two oppositely oriented field lines meet each other and what we call magnetically reconnect. So this is a well-known phenomenon in plasma physics, which powers, for example, solar flares, gigantic eruptions right at our own sun, which are powered basically by annihilation of oppositely oriented magnetic field lines. This has been a very active area of research in plasma physics, and in the last 10 years, we only got to know how this reconnection operates, at least in 2 dimensions in flat space-time. We got to know that this initially laminar structure where the two oppositely oriented magnetic field lines touch each other gets fragmented into pieces where the magnetic field gets basically bunched up. Like this are what we call magnetic islands, a local concentration of magnetic field and plasma, and this regions which we call X points, where the magnetic field actually goes through zero and where the magnetic field lines are actually reconnecting. So the field lines are actually reconnecting inside the X points, and the result gets advected into this big blobs of plasma flying around. So exactly the same phenomena happens at the equators of this, what we call magnetospheres, the surroundings of black holes. An interesting side effect that we found in this study is that this current sheet is a source of another energy extraction mechanism. So what we described in the Blandford-Znayak mechanism is that we learned that the rotation of the space-time in this jet field line region twists up the magnetic field, and this launches an outflow of charged particles and plasma. Penrose in 1969 hypothesized about a different mechanism, where he basically assumed that if a particle flying through the ergosphere could be disintegrated into 2 different particles, one of those particles could get into a very interesting trajectory, which if an observer at infinity would measure its energy, would mean a negative energy trajectory. And then as this charged particle, or just actually a neutral particle, can get advected into a black hole, the total energy in the black hole will be diminished. So the particle that gets escaped to infinity has the energy higher than the original particle flying into ergosphere had. So Penrose assumed that this happens via this disintegration of a particle in the ergosphere, where he did not actually say how this disintegration can happen. What we found is that this current sheet provides the disintegration of charged particles sort of naturally. So the byproduct of this magnetic reconnection process is that there is a very strong electric field operating right at the point where the magnetic field goes through zero. And this electric field works basically like a Penrose agent. It separates particles according to its sign. The positive sign particles go along the electric field. The negative sign particles go oppositely to the electric field. And this electric field works as an agent that splits the electron-positron pair, which gets advected into a current sheet, into 2 different particles. And turns out that one sign of the particle gets advected into a black hole and can get on this negative energy trajectory as seen by observer at infinity and swallowed by the black hole. This extracts the energy of the black hole and pulls out the other particle, the positively charged particle, to infinity along this last field line, which penetrates the ergosphere. The similar process can also operate very close to the event horizon in the jet region, although this current sheet is much more efficient in powering this Penrose process. This has been recently confirmed by analytical study by a postdoc at Columbia, Luca Camiso, and his co-author in a recent paper that also got a lot of press coverage, where they basically assume that this current sheet exists and used all the knowledge that we accumulated about magnetic reconnection and came out with a very detailed theoretical explanation of how this Penrose-like process may operate in current sheets around black holes. This is just a cartoon picture to visualize what I told you in words, that visualizes the original Penrose process. The particle coming to the ergosphere gets split into a pair, disintegrated right here. One of the particles get advected into a black hole in the state with a negative energy. and the other particle gets attracted to infinity with an energy that is higher than the energy of the initial particle. Actually, this process is entirely classical and can be observed with acoustic waves in the lab, which is a very interesting paper from recently in Nature Physics. You can ask me in Q&A section about how you can observe this process with acoustic waves. So this is a more quantitative diagnostics of this. The different curves here show the energy flux of different components. The gold line shows the Poynting flux. This is the highest component in the system. This is the flux of electromagnetic energy powered by the Blanford-Znanek process. And the blue and red curves shows the energy flux of electrons and positrons. So this is the same plot, but as a function of time at a given position in space, where you see that instantaneously you can get a very high power energy fluxes driven by the particles. This is when these big blobs of created in the current sheet, which I called magnetic islands, got swallowed by the black hole. The black hole at that point, it's a lot of energy, negative energy particles, and a lot of energy gets extracted. So the simulations basically showed how those two different processes, the purely electromagnetic process of energy extraction of Blanford and Znanek that powers jets, can coexist with Penrose process operating in the reconnecting current sheet. So now I'm turning to a second subject, which describes how the plasma is created in the first place inside those jets. So in the previous simulation, we basically assumed that the plasma source exists and studied how this plasma reorganizes the electromagnetic field into a self-consistent solution. Let's now do everything from first principles with one assumption that we assume that the magnetic field exists on a black hole. So let's neglect the accretion for now, and let's say the accretion did its job, brought the magnetic field onto a spinning black hole, and let's see what happens afterwards. So in this simulation, we're just modeling a patch of a black hole with a radial magnetic field, and just saying what happens with the photons and charged particles. So this simulation self-consistently tracks not only electrons and positrons, but also photons. These photons can interact with the photons from the accretion flow, which is also assumed, by the way. And these two collisions of two individual photons can create electrons and positrons. So let's see how the resulting solution looks like. On the left, you will see the dynamics of photons, and on the right, you will see the dynamics of the plasma density, the density of electrons and positrons. So you basically see that instead of a laminar flow that we got in the previous picture, we get this very intermittent production of individual clumps of electrons and positrons, which are escaping from the black hole above certain radius and flow back towards the black hole beyond this white surface. So this is a surface which we found to be very important into where this process operates. This is what we call an inner light surface, a surface at which in this electromagnetic solutions, basically this surface imposes a causality on plasma. Beyond the surface, all the plasma particles have to go towards the black hole because electromagnetic field tells them to do so. And above the surface, the plasma particles can escape to infinity. So the surface tends to be a natural place where this lightning happens. And the physics of this is pretty simple. For a certain time, you create a state, for example, right here, where the plasma density is very low. When the plasma density is very low, we get in a situation basically like a vacuum. In a vacuum, we know that the spinning black hole has a lot of electric field. So in that particular piece of space, you got a huge chunk of electric field, which if you put one stray electron or a positron, it can get accelerated to very high energy, create new photons, and this avalanche process that I described before starts. So this is what I call a lightning. Out of one particle, basically in a localized piece of space, you create a bunch of particles that then basically start to back react on the electromagnetic field. And they do entirely what the plasma wants to do with the electric field. Positrons go along the electric field, electrons go in the opposite direction. They screen the electric field, which was accelerating them in the first place. And this means that the electric field cannot exist there for a very long time. It would get screened by electrons and positrons, and the whole lightning process would have to stop for a while. So this is why it's intermittent. You get an individual cloud of electrons and positrons, it escapes. Also, the particles that are left behind this cloud get absorbed by the black hole. And only once this whole thing clears out itself, you create again a state with very low density of plasma, which could start the lightning again. So this is an intermittent process that operates pretty much out of phase across the magnetic field lines. So in the end, you get a very sort of blurry and non-coherent state. Although if you would look into one individual field line, you would get exactly the same process that I just outlined to you. So this is a process that feeds these jets with electrons and positrons that could fly away to infinity, and something else will happen with them as they would fly to scales much larger than the event horizon. But this is how they are born right at the edge near the black hole. Turns out that this process cannot explain TeV flares from 87, basically because this intermittency gets blurred as we model this in 2 dimensions. In 1 dimension, the flaring type activity would be much more pronounced because it would be much more coherent. So our answer to this question is that probably to explain the real flares, you need to model global conditions. Unfortunately, right now, these kinetic codes cannot yet be scaled to 3 dimensions. The simulations are still very challenging. So what we've actually looked for to explain flares is to resurrect this fluid approximation. But instead, contrary to what people were doing before, we brought our plasma physics intuition and asked a question: what is the numerical resolution that is required to actually resolve any of this flaring dynamics? And the rule of thumb that the plasma physics formulated for us is a very simple relation between the length of the current sheet and the scale at which the electromagnetic field gets dissipated because of the plasma effects. So if this ratio is larger than 10 to the 4 roughly, then the reconnection would proceed in this regime, which I had outlined to you before, that the reconnecting current sheet gets fragmented into individual blobs of a magnetic field, and a lot of interesting dissipation of the magnetic field can happen. If you think about this in terms of numerics, you would think that, well, if your length scale is of order a few gravitational radii, you want to resolve this dissipative scale with, let's say, a few numerical cells. This basically means that the simulation has to be at least few thousand cube large. And this introduced a huge gap between what was possible, let's say 10 years ago, when people have been modeling the systems with resolutions of hundreds cube before, and what we would need, which is 2000 cube and larger. So this is a result of the largest ever fluid type simulation that's been run by a collaboration of people, including Flatiron postdoc Bart Ripperda and Matthew Liska and Kushik Chatterjee at Harvard, where we basically took Matthew's fastest code that can operate on graphical processing units. We took it on the largest computer in the world, operated by Department of Energy Agency Summit, and ran a simulation of a basically 3000 cube resolution. And this is a result which basically shows that the secretion flow can basically stop for a while, unlike what people thought before. So right now you see that there is this big accretion flow which was evolved for 9,000 light crossing times across the event horizon, well before I started this movie. And right at 9,000 Rg over C, you see that the matter is basically starts to get expelled out of the event horizon. So for example, right now, you start seeing that there is not much matter except for this equatorial flow in the very midplane of the disk. And this is where reconnection could actually operate. You have oppositely oriented magnetic field lines inside the jet. They would meet each other in this equatorial plane, reconnect, and could power observe flares. We don't actually even know how this looks in 3 dimensions because it's very challenging to visualize this data. How we assume this happens is that this current sheet is very non-axisymmetric. The accretion in 3 dimensions happens very non-uniformly in the azimuthal direction around the black hole. You get blobs of plasma accreting with basically wedges of low density where these current sheets could exist. So in this cut, you nicely see a current sheet happening right inside this equatorial plane. And this event is accompanied by a drop of the magnetic flux on the event horizon. So the magnetic field gets brought to the black hole by the accretion flow. It accumulates at some point, and then for a certain while, the magnetic field is so large that it stops accretion. And when it stops accretion, the only way to go further is to get rid of some of this magnetic flux. And getting rid of the magnetic flux happens through the magnetic reconnection right in this equatorial plane. So why this is interesting is because we think that the timescales and dynamics of this plasma actually matches with what gravity observes from Sagittarius A star. The time between flares is roughly 1,000 light crossing times across the event horizon. So for parameters of Sagittarius A star, this would be few hours, which is consistent with the recurrence time of X-rays and near infrared flares. The brightest flares would, like this one, for example, happening around 9,000 Rg over C, would last roughly for an hour. And most importantly, this big blob of matter, which is in this picture produced by the outflow from this reconnecting region, colliding with the black hole, would sit right at the right distance, roughly at 5 to 10 Rg away from the black hole. So the picture that we're imagining happening here is that the magnetic field of the jet gets reconnected inside this this current sheet in the equatorial plane. This reconnection drives an outflow of very energetic plasma that collides with an accretion flow around at a distance around 5 to 10 Rg from the black hole. And this is where the bright spot of matter would be produced and seen as the source of near infrared and X-ray flares. There is a lot of work to do, but this is a very sounding and very interesting, I think, advancement that allows us to move this forward. So how this would look like for M87? M87 black hole is much bigger than Sagittarius A star. The time between these flares would be still around 1,000 horizon crossing times, but for M87 mass, this timescale would be roughly a year. EHT, although, observed this black hole for roughly a few days. So it's interesting that if EHT observation would be lucky enough, it would actually capture the accretion flow right in this flaring state, not in this quiescent state where the accretion happens more or less time steadily, but in this state where the magnetic field cleans up a little bit of the accretion flow out and where powerful reconnection is happening. So right now, people are thinking about how to model the next generation event horizon telescope observations, which at least according to the program, are thought to produce movies in real time of how this accretion happens around the black hole. And if the program and the observations are lucky enough, I think in next 10 to 15 years, we could capture M87 right in this state. There is an interesting caveat in this story is that the rate at which the energy gets dissipated in this current sheet depends on the assumptions about plasma physics that I made. For example, in this fluid picture, we know that the reconnection is actually slower if you would unless if on the other hand we would take the full plasma physics effects into account. So we tested this is a much simpler experiment, which is relevant for another scenario, which, for example, is relevant if you think about the black hole neutron star merger, when the mass ratio of black hole and neutron star is high enough, the neutron star may not actually be disrupted by the black hole, but gets sort of swallowed as a whole piece. So if a neutron star gets swallowed by a black hole as a whole piece, what you end up for a certain while is that the magnetic field of a neutron star gets right on top of a black hole, and you end up in a situation which is similar to what happens at the event horizons of black holes in the center of the galaxies. So in that case, you would start from initially roughly dipolar field of a neutron star, and the Noether theorem, which is very well known for black holes, would tell you that magnetic field could not exist on a black hole unless there is a source. So since in that system there is no source, the magnetic field has ultimately has to leave the black hole. And what Ashley Bransgrove, a PhD student at Columbia, found with us is that this magnetic field would be basically reconnected through the current sheet, which happens in the equatorial plane of this black hole, and the magnetic flux would leave the black hole at a time comparable to a few hundreds Rg over C. And it's interesting that the rate at which the flux leaves the black hole depends on whether you model this with fluid assumptions or you model this with very first principle collisionless plasma simulations. So if topic for a future research is to understand how this lose of the magnetic flux on the black hole operates in a realistic, taking into account realistic plasma conditions around supermassive black holes. This is the last very short topic that I want to talk to you about. So we talked about this very large scale flares that are produced by large scale reorganizations of magnetic field and plasma flows around the event horizon. But there could be smaller flares, and particularly in near infrared, we know that the smallest flares are basically like a noise on top of a quiescent activity of a black hole. So this could be some smaller scale reconnection events which could happen inside this turbulent flow happening between the jet and the accretion flow. And this is where we would like to understand it at least locally, not even taking the black hole into account. So our predoctoral student at Flatiron, Sasha Chernoglazov, worked on trying to understand how relativistic turbulence can create current sheets. And turns out that as the non-relativistic turbulence, it's also very efficient at creating very intermittent, very elongated large-scale current sheets. And this is where another advancement in plasma physics of last 5 years comes into play, is that people realize that as you go down and down into turbulent cascade into smaller scales, these current sheets would eventually start to reconnect. And this would affect how the energy gets dissipated in turbulence. So this is even more challenging than resolving this gigantic current sheets that are standing right at the event horizon. These current sheets are hidden deep inside the turbulence, and to resolve them even in 2 dimensions, you need gigantic computational grids. Basically 64,000 grid cells is where you start resolving this physics even. And what Sasha was able also to push is that we can study this in 3D with much lower resolutions, basically with few thousand cube. And he was able to show that this very largest current sheets inside the turbulence also starts to get reconnecting and unstable to the formation of this big blobs of magnetic field, which we call plasmoids. So this is a very exciting frontier in both fundamental plasma physics and how to relate the consequences of this plasma physics to observations. So I'll end up with these conclusions, and instead of the conclusions, I would formulate an outlook, which I think is relevant for future years. We're right now opening the very exciting window into how plasma and charged particles, namely plasma and magnetic fields, fly around right near the event horizon. We have a very exciting observational windows. We have a picture of the Event Horizon Telescope. We have observations of flares right near the event horizon, and we know how to model them. So we know to model them with this new codes and algorithms which allow to model collisionless plasma in strong gravitational field. We would need to advance them a lot with new coming exascale computing architectures. We would need also to build an analytical theory which would allow to rescale the parameters of the simulations, which are obviously artificial compared to the reality. As I told you, we cannot model the actual density of the particles that are sitting in the black hole. we need to rescale all of these parameters. So we would need to find out clever ways of how to extrapolate these results of simulations to observational phenomena. However, I think in next 10 years, these are very achievable goals. And this is a very good good time window to think about how does this black holes produce the observed light that we see in the spectacular observations. And I'll stop sharing here, and we'll move on into Q&A section. Thanks everyone for your attention.